here. All right. Happy Friday. We'll be happier once it's over, I think. So I posted, well, I gave you handouts, but the handout is posted on Moodle if you want it. Cute color. I didn't print in color. That's insane. And I put together an assignment already, but then I thought about it, and there are 2 questions on there that I want to delete. So maybe don't start it yet, because then I have to. Well, it'll just wipe your work.
Also, if I accidentally close the door or something like
It'll just jump back in. It's fine. Yeah, it's pretty clever. And then we've got our test 2 on November 17th, which is what we were talking about. I'll add a note to the top here. Test number 2 is on November 17th. I don't think I need to put the year, but I did. Oh well. Hopefully I put the right year. So I don't know if you tried to read chapter 9, but man, is it dense. So long, so dense. So I decided to make some notes instead for us to fill in. And so it's straying from our typical format, but I think that you might like it because it's just a little bit easier this way. I hope. So we're gonna do chapter 9, which is graph theory. And then because I broke it down into almost nothing, just what you need, we'll do trees, which is the last chapter of the textbook. There's more material, but the last chapter of the textbook on Monday. And so I'll do the same thing where I bring notes for us to fill in, because it's also one of those really applied things that we're going to be working on. It's just a subgroup of graphs, special graphs. Okay? And so sometimes we call these networks, which makes sense if you are on the computer science side of things, right? And so when we think about networks, you can have your basic network, right? A network of computers, for example, but they all can be condensed into graphs. Okay, and so one famous example is the Königsberg bridges. Now, I'm not German, but I feel like something like that. I guess Königsberg doesn't exist anymore. And Steve was telling me, he's in my office. He, well, not right now. I keep him in my office. No. Steve was telling me, though, I guess at some point in a war, some of these bridges were blown up. So the problem is, kind of this famous problem is, you want to start a walking tour, and you want to cross each bridge exactly once without crossing it again. Okay? And you have to start at the same spot that you end up at. It's not solvable, so don't even try. I'll save you the trouble. Okay, so, but we want to talk about why it's not solvable. Okay, and so, but yeah, kind of fun to think. Well, I guess not fun. Definitely not fun. I take that back. But if you blow up some bridges, then it's solvable, right? So at some point in time, it was a solvable problem, but then they rebuilt the bridges because I think they like to not be solvable. Now, did I share my screen? It's always something. Okay, good. Phew. So the problem, and you have it, so you're going to start anywhere. and cross all the bridges exactly once and finish where you started. Okay, but I'll make a note here that this is not solvable. Okay. Which is a solution, right? Being able to say that it's not solvable because of this, and that's what Euler did. So Euler is this famous mathematician, and just so you sound like you know what you're talking about, you want to call him Euler, like oil, because otherwise you sound like you don't know what you're talking about. And so he developed this solution and established why it can't be solved. And that morphed into some topics in networks and topology and just kind of graph theory in general. So how he did it was he said, okay, what if we represent the land areas as vertices or nodes, right? So each land mass is just going to be a point, which I say you boil it down to just the blob, right? Got blob, 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 blob. So you've got a blob on this side. It's kind of cut off. It's not the greatest picture, but it's the one I had. A blob, and a blob. So we only have 4 blobs that we're working with. Only. And we can do something like we can call them A, and to match the graph that I have in my notes here, B, and then maybe C, and then D. All right. Thinking about, I guess I could have drawn them on top of here, but I didn't. Let's see here. So these are called vertices. Oops. And then we're going to connect them with edges or arcs or line segments. And without scrolling up, I'm just going to do what I have here because I know it's right. And then we can confirm. So the network or the graph is going to look something like this, where these are the arcs or the edges, if you prefer. This is called a network. Or a graph. Or edges, but I did a poor job. Edges. And what's the color I haven't used? Light blue. These are called regions, of course, which I think if I asked you how many regions are there, you would be able to tell me without me defining it to you or for you. But one of the things to note, these are regions, but the outside is also a region. Okay? Note the outside is also a region. Oh, here, let me do this. So if I have my A blob, and I called this my B blob, C blob, D blob, then I had A to C, A to C, C to D, C to D, D to B, C to B, and A to B. which I'll make a copy of and just put it over here, put her there. But I made a less fancy version of that. So that's where this came from. There. Nice. Okay. So that was the first thing that he did. And I don't know, I should have done more research if it had been done before, kind of to establish relationships, probably. I'm assuming it had. We say a graph is connected, okay, if there's at least one path between each pair of vertices. Now, it's possible to have a graph where you have maybe some set of vertices that aren't connected, and that's okay, but that's not what we're dealing with, right? So that is a potential graph, but we're going to be talking about connected graphs mostly. Okay? And so if there's at least one path between each pair of vertices, right, so you can get to all the vertices some way, then it's connected. So then this problem, right, the problem was, okay, we want to start, and then I want to cross each bridge exactly once and end up where I started, okay, which is now what we call an Euler circuit. Okay. A circuit because we're starting at one point and then we're going back to that point, right? And we're going through all the edges exactly once. So begin at some vertex, any vertex, travel on each edge exactly once, and then return to the starting vertex. That's the definition of an Euler circuit. Okay? And so we can rephrase the Königsberg problem as, does this graph have an Euler circuit? Right? And so he deserves it. He came up with the solution, or the fact that there is no solution. And so we call it an Euler circuit. Okay? So can we have an Euler circuit? Here we go. One of the things to build up to the solution here is, let's just practice counting the edges, the vertices, and the regions of these guys. Now, I'm going to set up a little table down here, and I'll do A, B, C, D, E, F. And we want to know the edges of these things, number of edges, vertices, and the regions. I'll just add some lines because what a mess I'll make if I don't. Not terribly straight, but whatever. There. Okay, so counting the edges in A, pretty simple. 1, 2, 3. In B, I have 1, 2, 3, 4. So I've got 3, 4. In C, we have more. 1, 2, 3, 4, 5. Okay. 4. 1, 2, 3, 4, 5. Sometimes I have to count them. And finally, 1, 2, 3, 4, 5, 6. How about the vertices? 3, 3, 3, 4, 4, 4. Boring. 3, 3, 3, 4, 4, 4. How about the regions? 1. Or I guess, sorry, the outside is a region 2. That throws me off. So 2. 1, 2, outside, 3. 1, 2, 3, outside, 4. 1, 2, 1, 2, 3, 1, 2, 3, 4. So 2, 3, and 4. One relationship that's kind of interesting is that we can notice that the relationship between the vertices and the regions minus 2 is going to be the number of edges. Okay? So you can confirm that, and that's just an interesting thing. There's probably a crazy proof in the textbook somewhere why that's true, but I don't really care. But we can go through and confirm it. So we've got 3 vertices and 2 regions. So 5 minus 2 makes 3. And so what we're going to find is that 3 plus 3 minus 2 is 4. And it should just all equal the number of edges. So, or what we could say is that V plus R minus the number of edges has to be 2. Just rearranging that. That's just a little fun thing. So one of the things that we're going to talk about is whether a network or a graph is traversable. Okay. It's traversable if it can be traced in one sweep without lifting the pencil from the paper and without tracing the same edge more than once. Okay. Vertices may be passed through more than once, right? So you might be able to do something like, oh, I can go into this vertex here, and then I can, well, how can I do this? It's kind of hard. I can go through here, and then I can go through this vertex here, and then I can head down this diagonal, right? So I'm allowed to pass through the vertex more than once. It's the edges that I'm concerned about. But Emily, I wish we could be concerned about the vertices as well. Don't worry, that's a Hamiltonian circuit per cycle. So we're going to do both. Okay. So the degree of a vertex is the number of edges that meet at that vertex. And that's going to be a key thing that we think about, okay, because it's all going to come down to the degree of a vertex. Okay. And so from there, we can classify a vertex as even or odd, depending on its degree. And just as a side note, we say 0 is even. Just if you have 0 vertices, or sorry, 0 edges heading into a vertex. So if you have a situation like this, right, for this graph, this one has 0 vertices, or sorry, 0 degree 0, which is even. Yeah. Degree 0 is even. Okay. So just as an example, if I have a vertex that looks like this is of course degree 3, which means it's odd. A little fun fact in LFF, the sum of the degrees of the vertices will always be twice the number of edges, right? Because each edge goes to a vertex, right? And so then right? If you've got this edge here, then of course the number of vertices is 2 for every edge, for every arc. Now, if a vertex is odd, it must be a starting or an end point. Yeah. Therefore, we can only have up to 2 odd vertices for a graph to be traversable. So that's what we're concerned with in this scenario, is whether it's traversable or not. Okay. So we can only, I'll highlight this whole thing. We can only have up to two odd vertices for a graph to be traversable. Okay, so I'm going to squeeze it in here. We state without proof because no thanks. By the number of odd vertices, right? We're told that we can have up to 2 odd vertices. And so our options are 0, 1, 2, and then I just lump everything else into 2 plus because it's not going to be traversable, right? We were just told up to 2. So then the number of odd vertices and whether it's traversable or not. If it has 0 odd vertices, then you hit a gold mine. It is traversable, meaning, right, you can count the number of vertices or the number of odd vertices. And if you don't have any odd vertices, then you know you can draw one line throughout, going through each edge exactly once. Right? So that's good. Where would you have to start? Well, you can start at any point. And in order for it to be traversable, which is oh, it doesn't actually say, but I think that might just be me being sloppy, but maybe not. I'll just say at start. Right. I'm forcing it to go back and make a loop or a cycle. If you have one odd vertex, it's not traversable, which means you can't do it. If you have 2 odd vertices, it is traversable, and you're going to start at the first odd vertex, which is up to you to decide, but then you're going to end, okay, so it's not a cycle. Then you're going to end at the second odd vertex. And then if you have 2 or more, we were just told it's not traversable, so there's nothing you can do. This is going to be very helpful in figuring out the Königsberg problem, right? Why isn't it solvable? Well, we can count how many odd vertices we have. Now let me just copy. I'll copy. Should I copy my fancy one? It looks so good. Copy? Why not? So if we look at vertex A, B, C, D, we can figure out the degree of each of them. A looks like degree 3 to me. Uh-oh. We can only have, well, if we have 1, we have to have 2 odd vertices, right, for it to be traversable. And so, all right. Vertex B is also degree 3, so that's okay, as long as C and D are not odd. But C has degree 1, 2, 3, 4, 5. Oh. And D has degree 3. Since we have 4 odd vertices, 4 odd vertices, the graph is not traversable. I'll clean that up. It is not traversable and therefore not an Euler circuit. Oops. Disrespect Euler like that, writing his name wrong. So it's traversable if you can cross every edge exactly once, right? You're allowed to go through a vertex more than once, right? But each edge is crossed exactly once. But it's an Euler circuit if you can start and end in the same spot, right? Hence the circuit. So Euler's circuit theorem says that every vertex on a graph, and this is a bastardized version of it, but every vertex on a graph with an Euler circuit has an even degree. And so you have to have an even degree. And conversely, if in a connected graph, every vertex has an even degree, then the graph has an Euler circuit. So you can only have an Euler circuit if you only have even degrees. It's traversable, yes, if you have 2 odd vertices, right? That's what we just established. Well, I stated without proof, right? We know that it is traversable if we have 2 vertices, but in order for it to be an Euler circuit, you can only have 0 odd vertices. Okay. Oh. So the next example, is it traversable? We'll start with A. It's traversable if you have 0 or 2 odd vertices, and that's it, right? And so here they've even counted the degree of the vertex, right? And so here, this is showing that it's degree 2, right? Which you can confirm, but it's actually giving the degrees, which feels like cheating. You can count. 2, 4, 4. 4? Did I say 4 3 times? But 3, 3. Okay. We'll allow it. It's traversable because we can have 2 odd vertices, right? That's allowed, but it can't be an Euler circuit. So here, this is traversable. But not an Euler circuit. What about the next one? It doesn't look good, does it? 3, 3, 3, 3. No thanks. 2, 3, 4. Not traversable. Oops. So it's definitely not an Euler circuit. Have you guys talked about the traveling salesman problem? I changed it to salesperson because cool like that. But have you talked about that problem before? It's also one of those problems that there's no, there are lots of solutions, but they're still improving the solution. And so it's a well-established problem. And I put the link to, well, it's kind of outdated now, but when I found it, it was relatively new. And so after 44 years, there's finally a better way to find approximate solution to the notoriously difficult traveling salesperson problem. Okay, so the traveling sales, and of course, computer scientists break traveling salesperson records. So it is a thing, and there are people out there working on it, showing off. And so what is it? A salesperson starts at home and wants to visit several cities without going through any city more than once, and then return to the starting city. Okay. They would like to do it as efficiently as possible. Now that could mean minimize the distance, or minimize the cost, or minimize the time, right? So there could be different variables that we're looking at. But for us, we're going to focus on just distance, because why not? Usually minimizing the distance also minimizes the cost and the time, right? With some exceptions. But what's this doing? Now we're interested in the cities, which we would consider the vertices, right? We can think of the vertices as the cities, and then the roads that connect them as the arcs or the edges. And so we've just kind of flipped the script. So this is basically I shouldn't say just, but the idea is simple. The application, not so much. Just reversing the edges and vertices in an Euler circuit. Right? Euler circuits we only wanted to go through each arc once. We were allowed to pass through vertices as many times as we wanted, right? But the condition was that I start and end at the same place, and I can only cross each arc once, exactly once. But now we're doing the same thing, but we're talking about the vertices instead, which means I'm allowed to recycle through edges, but that's going to be hard to do if you're not allowed to cross through the same vertex, right? But this is what we call a Hamiltonian cycle. You're going to visit each vertex exactly once and end at the starting vertex. So it's still a cycle. You're going to go through and just different criteria. So using one of the graphs that we had earlier, can we find a Hamiltonian cycle for this network? Now, this is one of those things where it would be so cute for me to give you, time to try to figure it out. But, and go for it, try it. It's going to take some trial and error, likely, right? How about I give you a hint? I know I'm acting as if I'm not going to give you time to do it, but then I want you to do it. How about you start at A? And then I'll label these B. I don't know why I have this as C, but I do, so let's just stick with it. And then that's D. So the rules of the game are you want to hit each vertex exactly once, and you want to start and end at A. I'll give you the starting point. Now I'm telling you to start and end at A, but you could have started and ended at any point if you want to, but I'm gonna start and end at A. And there's lots of different solutions. One of them, to me, the most obvious would be from A to B, and then maybe C to D, because I like it in alphabetical order, and, or sorry, B to C, and then maybe C to D, and then D to A. So then I would have A to B to C to D to A. One Hamiltonian cycle. There are many other options. Okay. Good. What if we have this graph, and instead of making you figure out a Hamiltonian cycle, because that would be rude, I want you to decide if each cycle is Hamiltonian A to B, which would look like, oh, maybe I can do this, or I know I can do this. Copy. I'm just going to use this to draw out each path that we're asked to look at. Yeah. Key things, you have to start and end at the same point, right? Otherwise, it's not a cycle. And so right away, start and end at the same point. That's good. So good start. And these do not. So I can cut that right away. You don't have to worry about it. Right? Eliminate it. B to B, that's good. So now we can check the other condition. What's the other condition? You have to hit each vertex exactly once. And so here, if I go from A to B to C to D to A, this is not a Hamiltonian cycle. I'm just going to define that here because I don't want to write it out a bunch of times. Right? Since E and F are not included. So that's not a Hamiltonian cycle. We already said, okay, well, this one, right, it might hit every vertex, but I haven't even tried. But you have to start and end at the same spot. And so how about here? Okay, they start and end in the same spot. And what am I going to do? From B to C to D to A to E to F to B. Yay! I hit every vertex. Includes every vertex exactly once. Therefore, it is a Hamiltonian cycle. Nice. Okay. So like I was saying, unlike Euler circuits, there's no solution deciding whether a network has a Hamiltonian cycle. So there is no check-in point that we could use, right, to decide if there even is a Hamiltonian cycle worth pursuing. So that's kind of a problem. And then I mentioned the link, which I already showed you. But there are many different methods of solving the traveling salesman problem, but not all are optimal. So usually you kind of run through different methods and figure out the optimal solution. So the first method that I want to introduce is called the sorted edge method. Now it looks like there should be something here, but that's just weird spacing on my part. Sorry about that. So the sorted edge method goes a little something like this. You're going to draw a graph showing the cities and the distances or the cost or the time, whatever you want to optimize. You want to optimize. Okay. And you're going to identify the starting vertex. Often it's given or you have some good idea of where to start. Okay. And we're doing the sorted edge method, which says that, okay, so because this is all the same for any method, you draw your graph, you lay out your constraints, right? The distances or whatever, and then you pick a starting vertex. So that's going to apply to any method, I guess. But then the sorted edge method says that you're going to choose the edge attached to the starting vertex that has the shortest distance, like lowest cost or time generically, right? But just the shortest or the smallest weight. Okay. And then you're going to travel along this edge to the next vertex. Okay. Fair enough. What are we doing? We're sorting the edges as we go, right? I'm going to go for my smallest edge. So then at the second vertex, you're going to travel along the shortest edge. Again, you cannot go back to a vertex that you've already visited, which of course includes the starting point. Or maybe it's not that important. Includes the starting vertex, because that would mean that you're done, but you can't keep going to you can't go to the starting vertex until you're done. So then you're going to continue until all vertices are visited and you arrive back at the starting point. Yeah. So one of the things that I want to note here is that the sorted edge method may not produce the optimal solution. Okay. The nearest neighbor method says you're going to go to the nearest neighbor by distance or cost or whatever. And you can't go back unless it's to the starting vertex after going through all the other vertices. Now that I think about it, it's kind of the same. And I think maybe the nearest neighbor, did I add to the after going through all the other vertices? I don't remember. Maybe you're allowed to head back home before you're done, but that doesn't sound, that's not a solution. You have to hit all the vertices. Anyways, we're going to do an example of all of them anyways. Or you brute force and list all your possible options. So you check all your possible routes, and while you're off the hook for the reverse of the routes, because the distance or the cost or the time should be the same, so you can ignore kind of heading back in the other direction. Now, if you think about 4 cities, right? So 4 vertices, we know how to figure out how many different options there are, right? Because you have 3 cities that you can go to from your first vertex, right? If there are only 4, then you have 3 options that you can go to. And then from there, you only have 2 because you can't go back. And then after that, you only have 1 option. So in general, you're going to have n-1 factorial or 3 factorial routes, which means you have 6 routes to choose from. But half of those are reversals of the other. So there are 3 unique routes. Well, in terms of distance, time, whatever. know? So if we think about n cities, right, then I have n minus 1 times n minus 2 all the way to 3 times 2 times 1, which is n minus 1 factorial. We just established that. But that means that I keep half of them, which means I have n minus 1 factorial divided by 2. One thing to keep in mind, though, is if you're going to brute force something, that's going to get really, really unreasonable for large values of n, right? So if you're trying to map a route across the states and you've got, I don't know how many cities, at least 50, right? One, at least, probably more like 100, then there's a lot of different routes that you could take, and that sounds terrible. So just as a side note, for large values of n, this becomes unreasonable. Now I had to list the distances in this example because I didn't have the image. So, but I'm going to draw the image for you. But I think maybe I did it. A salesman wants to visit 4 California cities: San Francisco, Sacramento, which is 96 miles northeast of San Francisco. They're all going to be relative to San Francisco. San Jose, which is 51 miles southeast of San Francisco, and Fresno, which is 189 miles east of San Francisco. It's going to look something like this. So if I have San Francisco here, then maybe I have Sacramento up here, which I'll call S, I guess. So many S cities. San Francisco, SF, San Jose, SJ, and then Fresno is going to be way out here. I'll call it F for shorthand. So we were told that the distance between San Francisco and Sacramento is 96 units, miles, presumably, considering where I stole this from. San Jose was 51 miles southeast of San Jose, and then I'll just draw out the rest of the distances. Fresno was 189 miles from San Francisco, and then Sacramento is 129 miles from San Jose, like that. And then the missing links are these. Sacramento to Fresno was 173. And San Jose to Fresno was 151. Okay. What is the shortest trip starting and ending in San Francisco that visits each of these cities? So here we want to start and end in San Francisco. Okay, so I want to do it with the sorted edge method, the nearest neighbor method, and the brute force method. It's not going to be too bad, right? 4 vertices means I'm going to have 3 factorials, so 6 possible options divided by 2. So there's only 3 to brute force my way through. So it's not too bad. But here are our solutions. So my first solution is going to be the sorted edge method. The sorted edge method said that you're going to start so choose an edge attached to the starting vertex, which is San Francisco in this case, that has the shortest distance and then travel along this edge to the next vertex, and then keep going until you're ready to head back. Fair enough. So from San Francisco, my options are 96, 189, or 51. I'm gonna have to go for 51. How I'm gonna denote that is I'm gonna go from San Francisco to San Jose, and that's gonna cost me 51 miles. Or something like that. Now I'm sitting here at San Jose. I'm not allowed to go back to San Francisco until I'm all done, so I can't go there. And so then my next option, I'm choosing the shortest distance or the smallest edge, which is going to Sacramento. Sacramento S, which is 129 miles. So now I'm sitting here tempting to go back to San Francisco, but I can't because we have to go to Fresno. And there's only one way to get there, 173. Why is there only one way to get there? Because I can't go back to San Jose, right? That was one of the rules. I'm only allowed to go through each city once. So this was 173 miles. And then finally from Fresno to San Francisco, I'm allowed to head back because I've hit them all now. And I'm gonna go 189. So the total distance is 51 plus 129 plus 173 plus 189, which is 542 miles. How about the nearest neighbor method? It's going to be the same, in case you weren't convinced already. The nearest neighbor method says, go to the nearest neighbor. You can't go back unless it's to the starting vertex. And then I'm not 100%. I feel like you have to go through all the other vertices. I guess my question is, I don't know, I can't remember if that's something I made up or got from somewhere. Whether you have to go through all the vertices, or if the nearest neighbor is the starting point, do you just loop back? That doesn't make sense though. I feel like you have to hit all the vertices. Otherwise you haven't solved the problem, right? So that's probably why I have that there. Starting in San Francisco, again, nearest neighbor is San Jose. Nearest neighbor from here is Sacramento. Nearest neighbor, surprise, surprise, is Fresno. Back to San Francisco. It's the same. I'd be curious to know if they're ever not the same. I'm just going to copy this, so I don't have to write it out again. I don't know. It feels like something to Google. I don't know. I just did it blindly. And there's got to be a difference. Why would we? Why? I wonder if you have multiple edges. No, that still doesn't make sense. Is anyone able to get a Google out of that? What's the difference between sorted edge method and nearest neighbor method? While you do that, we know the total is 542 miles because it's the same. They're different methods because they have different names, but dang it, it's not coming to me. Anyways. How about brute force? Okay. I'm gonna grab a mini version of our graph because otherwise it's way too hard to visualize. But if we're brute forcing this thing from San Francisco, well, we know I can go to San Jose, Sacramento, and Fresno. That is one of the options, so we have to list it. So I'll copy this. And we know that that has a total distance of 542 miles. So that's the same. And also, it's the same in reverse, same distance in reverse. Right. It is an option to go from San Francisco to Fresno to Sacramento to San Jose back to San Francisco, but the distance would be the same. So we beat that horse. How about a freshie? How about San Francisco, not San Jose? How about we go to Sacramento? Why not? That's an option. Going to Sacramento is 96. From Sacramento, what if I go to San Jose? Why not? Which is 129. And then from San Jose, I'm going to go to Fresno, which is 151, and then back to San Francisco, which is 180. Notice that the path of San Francisco to Fresno first, right? And then either to San Jose or to Sacramento, it doesn't matter, because if you're looking at these in reverse, you are going from San Francisco to Fresno, right? And so you don't list those. And so that's why I'm avoiding those, because they've already been listed here in the backwards scenario. Okay. And the last unique option, remember we had 3 that we're going for. Oh, the total distance here was 565 miles. Out of these 2, this is the better option, right? It's shorter, and that was our goal. Okay. But what if we go San Francisco to Sacramento, still 96. Then what if I mix it up and go to Fresno, 173? And then I go to San Jose from there, 151. And then go back to San Francisco, 51. Ding, ding, ding. That's going to be 471 miles, which is clearly the optimal solution. Out of all the solutions, 471 miles is the shortest distance. Therefore, it is the optimal solution. So even when we have methods like the nearest neighbor, the sorted edge method, none of those got us to the 471, right? So they're methods, right? It's a way of methodically figuring out some solutions, right? But that's the unfortunate part of this problem, and that's why it's still unsolved, is there's no one method that will always get you the optimal solution. And that's a bummer, but also kind of fun to think about. And that's what you need to know about graph theory. For now. You'll do more later, but leave that for 251 or 221 or whatever you're calling it. Whatever you crazy kids are calling it. Any questions? No? Okay, well, that was earlier than I anticipated. Any objections? I release you. Have a wonderful weekend. And I'll go delete those questions that I didn't like from the assignment, and then you can try it. How about that? All right, stop this here.